Okay, so now we're going to take a look at the beam and the instrumentation. So we have an aluminum beam here, and it's instrumented with accelerometers. We have an accelerometer here, here, and here. Each one of those is a piezoelectric device that puts out a charge in response to acceleration that it senses. The charge then comes out through the coax cable here and runs into an amplifier into the computer system for data acquisition. We're going to measure the length of the beam first. And what we're going to do is take the free length of the beam. Now this beam is measuring in at, the free length is about 11 inches. So that's 11 inches. And my tape measure, you can see, has graduations on it that go down to a 32nd of an inch. So a resolution is equal to 1/2, or actually the resolution is 1/32 of an inch, but the error due to that resolution is 1/2 of that. So our error there is 1/64 of an inch. So we've got 11 inches free length on the beam. And I point out free length, I want to emphasize that because there is about an inch of this beam that's down in the fixture that we don't care about. And so we want to make sure that we're just measuring the free length of the beam because that is what's going to cause it to vibrate. Now, Dr. Bennett was going to talk a little bit about the fixture, and so I'm going to let him talk about that.
All right, we're just going to take a quick look at the mounting fixture here for the beam itself. As you can see, it's made up of this circular piece here of the fixture. That's bolted directly into the shaker table. And then there's this extra fitting here, which is used to clamp down onto the beam. And as Professor Zwick just described, that means that we lose about 1 inch of our free length of the beam. So in our analysis, we're just going to assume that this beam is basically fixed directly to the shaker table. But obviously in reality, we have all of this extra gubbins going on here, which acts as kind of like a dampener, if you like, between the beam and the shaker table itself. So no matter how hard we tighten down on those bolts in there, we're always going to get a little bit of dampening effect going on just because of this fixture itself. The other thing that we need to do, the other measurements that we need to take are the width of the beam in a few locations. So we're going to do the top, the middle, and the base. We're also going to take dimensions of the thickness at the top, the middle, and the base as well. We're going to do that using some calipers, and we're also going to weigh the beam as well. Alright, so we're just going to take a little bit of a closer look at the accelerometers and firstly how they're affixed to the beam sample. So what we use here is just a little bit of wax on the end of the accelerometer there to stick it to the beam temporarily. It's very important not to use too much of this stuff because again, if you have a layer of wax in between the sensor and the beam, we might get some more dampening effects there too. But then, on the other hand, we need enough to stick it firmly to the beam. So, Professor Zwick talked a little bit about those locations and the corresponding channels for each of those. You can see that they are labelled channels 2, 3 and 4. Channel 1 is our input frequency measuring exactly what the table is doing. And each one of these sensors has their own little data sheet in their box associated with them. And for example, the sensitivity here, as you can see, is what's used to calibrate the code which runs the software controlling the sensors.
One thing I want to point out too is that these wires that come off of the accelerometers, during the test, they'll tend to flail around quite a bit unless they're anchored down securely. So what we like to do is use tape to secure the wires to keep them from pulling the accelerometers off of the beam.